Welcome to our deep dive into the fascinating world of 3D magnetic structures.
We'll be looking at a research paper that presents a new method for visualizing and understanding these tiny but crucial components of future technologies.
We'll be exploring the paper, Three-Dimensional Model-Based Iterative Reconstruction of Magnetization in a Nanowire Structure, using holographic vector field electron tomography measurements.
It might sound a bit intimidating, but we'll break it down together.
Imagine being able to see the invisible forces that govern the behavior of magnets at the nanoscale.
That's exactly what this research is all about.
Let's start by discussing the significance of these 3D magnetic structures in fields like spintronics, data storage, and even machine learning.
These technologies have the potential to revolutionize computing and data storage, making them far more energy efficient.
But visualizing these structures is a challenge because they exist at the nanoscale.
While X-ray techniques have been used, they have limitations in resolution.
That's where electron microscopy, specifically a technique called holographic vector field electron tomography, or H-VFET, comes into play.
H-VFET relies on the Aharonov-Bohm effect, which describes how electrons are affected by electromagnetic fields.
This allows for much higher resolution images of these magnetic structures.
Now, this research paper introduces a new algorithm called Model-Based Iterative Reconstruction, or MBIR, to process the data from H-VFET.
This algorithm helps reconstruct 3D magnetization maps, providing a detailed picture of the magnetic forces within these tiny structures.
To test their method, the researchers built an L-shaped cobalt nanowire using a technique called focused electron beam-induced deposition.
It's essentially 3D printing, but at the nanoscale.
They then used H-VFET to capture data from the nanowire at various tilt angles.
Think of it as taking snapshots of the nanowire's magnetic field from different perspectives to build a complete 3D picture.
And this is where the MBIR algorithm comes in. It processes this data, minimizes errors, and creates a 3D map of magnetization within the nanowire.
The results were fascinating.
They were able to visualize different magnetic domains within the nanowire, each with its own unique magnetic properties.
They even observed a vortex domain wall, a boundary between two different magnetic domains.
These domains and walls play a crucial role in determining the nanowire's magnetic behavior.
And understanding them is essential for designing future spintronic devices.
The technique's resolution is remarkable. It can resolve features down to 50 nanometers.
That's incredibly small. But the researchers believe they can refine their method even further to study even more complex magnetic structures.
Structures like skyrmions and hopfions hold immense promise for next-generation computing and data storage.
Being able to visualize and manipulate these structures could lead to groundbreaking technological advancements.
It's an exciting time to be at the forefront of magnetic materials research.
And this paper offers a glimpse into the incredible possibilities that lie ahead.
The implications of this research go beyond just visualizing these tiny structures.
It could revolutionize data storage,
We could be looking at storage devices with much higher densities and speeds.
all while using less power.
Exactly. Energy efficiency is a key advantage in spintronics.
Why is that so important?
Because spintronics manipulates the spin of electrons instead of their charge.
Which makes it inherently more energy efficient than traditional electronics.
Especially in a world increasingly focused on energy conservation.
So the applications of spintronics go beyond data storage.
Absolutely. It can be used in logic devices.
The building blocks of computers.
And sensors. Imagine sensors that are so sensitive they can detect the tiniest magnetic fields,
Revolutionizing fields like medical imaging.
leading to more detailed and accurate diagnoses.
And we can't forget about the impact on machine learning,
Spintronics could be used to create artificial synapses,
mimicking the behavior of neurons in the brain,
enabling the development of more efficient and powerful AI systems,
processing information more like the human brain.
leading to breakthroughs in pattern recognition and decision-making.
It seems like spintronics has a lot of potential.
It does, but there are challenges.
Like what?
Scaling up the fabrication of these nanoscale structures.
Going from the lab to mass production.
Exactly. It's a complex engineering challenge.
And ensuring these structures are stable and reliable over time.
They need to work flawlessly for extended periods.
So continued research and development are crucial.
Absolutely. The pace of innovation is rapid, and with dedicated effort, we can overcome these obstacles in the years to come.
What makes this research stand out in the field?
Their meticulous approach to validating their results. They carefully analyze the accuracy and resolution of their technique.
making sure their findings are reliable.
They also addressed potential sources of error and limitations, which makes their method trustworthy for future research.
And their development of the MBIR algorithm is a significant breakthrough.
It allows researchers to extract meaningful information from the complex data generated by H-VFET.
It's like a translator converting raw data into a 3D map that's easier to understand.
It also sparks a sense of wonder about the unseen forces that shape our world.
Reminding us there's so much more to discover.
The ability to see and manipulate magnetic structures at the nanoscale opens up so many possibilities.
It's an exciting time to be following this field.
As we witness the birth of technologies that could reshape our future,
In this deep dive, we've journeyed into the cutting edge of magnetic materials research.
we've seen how electron microscopy and sophisticated algorithms can unlock the secrets of the nanoscale world.
A world that holds immense potential for technological innovation.
The ability to understand and manipulate 3D magnetic structures opens up incredible possibilities for creating materials and devices with specific magnetic properties.
This research is a crucial step towards realizing those possibilities.
It paves the way for advancements that were once considered science fiction.
As we conclude our exploration of 3D magnetic structures, we leave you with a question to ponder.
If researchers can already visualize these structures at this level of detail, what might the future hold?
What new materials and devices could we create?
What boundaries might we break?
The possibilities are truly vast.
And the future of magnetic technology is brimming with potential.
This concludes our deep dive into the fascinating world of 3D magnetic structures.